Okay, here we are. So let's start by talking about acids. And we're going to start with some properties of acids, and then we'll look at some properties of bases before we get into just some hardcore reactions of acids and bases. And it says here that acids have a sour taste. I wouldn't recommend tasting something like sulfuric acid. That would be very dangerous. But if you think about something like vinegar, vinegar owes part of the tartness of its taste to acetic acid. And so vinegar contains an acid, which is acetic acid, but acetic acid is not a strong acid, it's a weak acid. Citrus fruits like oranges, lemons, and limes, they contain citric acid. Citric acid is also used in some candies like sour, I don't know, gobstoppers or something like that. Also, if you think about the tartness of a Granny Smith apple, that's a result of acids that's found in the apple. What else? It says it causes color changes in plant dyes. I'm never going to ask you about that, but if you look at different types of hydrangea, depending on the pH of the soil that you grow the flowers in, you can get pink flowers or purple flowers. What else? It says that acids will react with certain metals to produce hydrogen gas. And here's an example of hydrochloric acid reacting with magnesium to give you magnesium chloride and hydrogen gas. So this is H2 gas right here, which is a flammable gas. It also says, and that's actually what's being shown right here. So this is an example of, so this piece of metal here, this is magnesium, and then this is a solution of HCl in here, and you can see the bubbles being formed of the hydrogen gas in there. What else? It says that acids will react with carbonates and bicarbonates to produce carbon dioxide gas. So here's another example. We take that same acid, hydrochloric acid, and we react it with calcium carbonate. We get calcium chloride, water, and we also get what? Carbon dioxide gas. So that would also produce bubbles, right? Because carbon dioxide is a gas that would leave the solution. It also says here that aqueous acid solutions conduct electricity. Now, why would that be? It's because they are electrolytes. And so you can imagine that the stronger the acid, the better electrolyte it's going to be. So we'll put here electrolyte like that. All right, so properties of acids. So that's just a little bit about acids. Next, we're going to talk about the properties of bases. So it says here that bases have a bitter taste. So whenever you taste something bitter, for example, it says here soaps contain bases. I don't know if you've ever had your mouth washed out with soap, but that has a very bitter taste to it. And yeah, it says here that bases feel slippery. Now, I wouldn't recommend going around and touching any kind of bases because bases are very caustic. They can burn your skin quite badly. But basically, if you take, no pun intended, if you take a strong solution of a base like sodium hydroxide, for example, and you touch that with gloves on, with like nitrile gloves, it will feel kind of slippery. Anyhow, same thing as with acids. Bases can change the pH of soil, which can change the color of certain types of flowers. And it says here the same thing, that aqueous base solution can conduct electricity, because if you have a strong base, it's going to be an electrolyte. Okay, and we said that electrolytes enable conduction in a solution because of the ions that are present. All right, the ions that are present when we have an electrolyte. Well, let's move from there and let's talk about the history of acids and bases a little bit here. And the first kind of scientist to come up with the definition of acids and bases that was widely accepted is Arrhenius. So this is Arrhenius acids and bases. And you need to know that the definition of an Arrhenius acid is that Arrhenius said that an acid is a substance that produces H plus in water. Now you notice here that we have a hydrogen ion. So this is a hydrogen ion. We call it a proton, right? We call H plus a proton. And the reason why we call it a proton is if you think about a hydrogen atom, right? It only has one proton in the nucleus and then it has one electron. So if you remove that electron, what are you left over with? You're just left over with the nucleus. And that's why we call H plus a proton. Now, H plus doesn't actually exist in water. And you're like, what? It doesn't exist? No, it actually binds to a water molecule because H plus, the proton, is just so small that it interacts with the partial negative charge on the oxygen of a water molecule to make this ion, okay? And you have to know this polyatomic ion. This is a hydronium, and I'm going to talk a little bit about hydroniums this evening, so you have to be fully aware of what a hydronium is. And so the answer to what we're talking about is if we take a strong acid like HCl and we put it in water, what we actually have in solution is hydronium ions and chloride ions. Okay, so we don't have any H+, and you're like, what? You mean if I have a mixture of HCl and water, I don't even have any HCl? No, you don't, because HCl is a strong acid. It dissociates what? Completely. Okay? That's what the arrow in one direction refers to. It's complete dissociation. Now let's talk about the Arrhenius definition of base. So we'll move to the next slide. And Arrhenius said that an Arrhenius base is a substance that produces hydroxide ions in water. So if you take ammonia, so this molecule here, this is ammonia, and you put ammonia in water, what actually happens is that ammonia will take one of the protons from water to make ammonium. And what else are you left over with? You're left over with hydroxide, OH minus hydroxide, like that. Okay? So again, you have to know the Arrhenius definition of an acid. It's a substance that produces hydronium ions in water. And Arrhenius said that a base is a substance that produces hydroxide ions in water. Here's an electrostatic potential map of the hydronium ion, which is basically just a hydrated proton, because I told you that in a water molecule, it's a polar compound, right? Water is a polar compound. Oxygen is more electronegative than hydrogen, and so it has that partial negative charge, and that actually attracts to the H+, and what you end up with is H3O plus, like this. So H3O plus, like that. So a hydronium ion. All right, let's move on from there. After Arrhenius, okay, Bronsted came up with an even broader definition of acids and bases. And you're like, well, why do we need another definition of acids and bases? The reason why is because the Arrhenius theory of acids and bases, or sorry, I should say the Arrhenius definition of acids and bases, doesn't encompass all acids and bases. And so Bronsted, kind of gave a broader definition. And he said something a little bit simpler. He said a Bronsted acid is a proton donor. So remember, a proton is H+. So an acid gives up H+, and a Bronsted base is a proton acceptor. So something that takes H+. Here's an example. If we look at ammonia, and ammonia is a base. Why is it a base? Because if you look at what's happening in this reaction right here, we have ammonia plus water gives you ammonium plus hydroxide. Now, you might not have a knee-jerk reaction to think an acid. How would water be an acid? Well, water can, in fact, behave as both an acid or a base, depending on the situation. But let's pay attention, or let's watch closely here, okay? So what Bronsted definition of a base, okay, he said it's a proton acceptor. Where is the base, ammonia? Where is it going to get a proton? It's going to take it from the water molecule. Okay, so when it takes that proton and takes it over to the ammonia, what you end up with is NH4+. Now, why does that have a positive charge? Because a proton has a +1 charge. So if you take something with a charge of 0 and you add +1 to it, you get a +1 charge. The same thing is true when we think about the water. The reason that water is regarded as an acid in this reaction is because it's giving up a proton to the ammonia. And when it gives up the proton, the water goes from being 0, right, neutral, no charge. If it loses a +1 charge, it's going to be left over with a -1 charge. And that's why hydroxide has a -1 charge, okay? So it says here that a Bronsted acid has to have at least one ionizable proton. And we're going to look at types of acids in a second. But first, give me a thumbs up if you follow me this far. Just Arrhenius acid, Arrhenius base, Bronsted acid, Bronsted base. Nothing more than that. That's all we're talking about right now. We haven't gotten into anything super heavy. And if you're wondering, hey, Mr. Dion, are there other definitions of acids and bases? The answer is absolutely. There's also what are known as Lewis acids and Lewis bases, but we're not talking about those right now. We're just talking about Arrhenius and Bronsted. Well, here are some types of acids. Now, earlier on in the class, when we discussed nomenclature, we also discussed types of acids. Or sorry, we discussed acids. We didn't categorize them as types, except for strong and weak, okay? But here we're going to classify acids based on the number of protons that they have, the number of ionizable hydrogens. Notice that word, okay? I want to back up just to make sure you're on the same page with me. Okay? Notice that it says a Bronsted acid has to have at least one ionizable proton. That means that in some acids, not every single proton in the molecule is an ionizable proton. Not every single hydrogen atom will be able to make H+. Okay, that's all I'm saying. And you're like, give me an example. Sure, coming right up. Okay. So first, let's talk about types of acids in terms of the number of ionizable protons they have. So if you look at a monoprotic acid, okay, monoprotic acids, let's look at them all. The first one is HCl, okay, hydrochloric acid. That one's pretty evident, right? Because there's only one hydrogen in the molecule anyway. Okay, so there's only one hydrogen. It's an acid. Well, of course, it's going to give up the proton. So that's why we call it monoprotic. It's got only the one proton. It's a strong acid. Therefore, it's going to be a strong electrolyte. The next one, exact same ballpark. This is nitric acid, HNO3, a very strong acid. It's miserable to get burned by nitric acid. It's happened to me a few times. I think, again, it's pretty abundantly clear that there's only one hydrogen atom in the whole nitric acid molecule. So, yeah, of course it's going to be monoprotic. Okay, now nitric acid is one of those strong acids that I've asked you to memorize. So strong acid, it's going to be a strong electrolyte. The next one is a weak acid. This is acetic acid. Now, I want to caution you about acetic acid because if you're the kind of person who likes to poke around the internet or look at different books or whatever, you're going to see different ways of writing the formula of acetic acid. Now, I would not write it, Mr. Dion would not write it the way that is written here in the book. The way that I would write acetic acid is like this. I would say CH3COOH, okay? Sometimes you'll see it written like this, a little bit more condensed, CH3CO2H, like this. And what I want you to understand is that the proton that's on the very end there, that is the ionizable proton, okay? The protons that are attached to the carbon, these three protons, okay, not ionizable, okay? And later on in the class, when we start looking at what are called Lewis structures, I will go over the whole structure of acetic acid with you and explain to you why those other three protons are not ionizable. But for right now, you're just going to have to kind of take my word for it that acetic acid only has one ionizable proton. But what else? You see that there's a reversible arrow here. Again, that's not the correct reversible arrow. A reversible arrow correctly drawn would look like that. But anyhow, it's good enough. Now, since it's reversible, what does that mean? That means that it's a weak acid. It only partially dissociates. It doesn't fully dissociate, right? These two acids do full dissociation. This acid only does partial dissociation, like that. Okay? The next acids are diprotic acids. I know you can tell what that means. It means they have two protons. Now, there's only one example that's shown here, and that is sulfuric acid, H2SO4. So sulfuric acid has a total of two protons, right? What's going to happen is that when you have just H2SO4, sulfuric acid, it's a really strong acid. So it's going to be able to liberate a proton, right? One of the protons really easily, okay? Again, full, complete dissociation. So it's a strong electrolyte. But what you're left over with is this polyatomic ion, right? This is the hydrogen sulfate ion, okay? Now, what about this hydrogen sulfate ion? Well, sulfuric acid already does have two protons, so that means it can lose two of them, okay? But what happens is, once you form the hydrogen sulfate ion, it's got a negative charge. Okay, how eager do you think the hydrogen sulfate ion is going to be to lose the second proton? Protons are H+. and the hydrogen sulfate ion is -1, it's going to hang on to that proton like grim death. Okay, it's like, I like my positive charges, I'm negative, please let me balance out, because if I lose a second proton, then I develop a -2 charge. Okay, and that is why the hydrogen sulfate ion can lose its proton. It even shows it right here, but now it's only going to lose some of that. Okay, so the hydrogen sulfate ion is an acid, but it's a really weak acid. Okay, it's a really crummy acid. Okay, and we'll talk more about that as the class progresses, but I want to move on and talk about triprotic acids. The only really triprotic acid example I can think of that we ever talk about in this class is this one right here, phosphoric acid, H3PO4. Not a strong acid. All three of the protons in phosphoric acid, all three of them are ionizable, but for the same reason, when you lose the first one and you make dihydrogen phosphate, that's still going to want to hang it onto its protons. So the acidity is going to go from weak to weaker to weakest as we go down like that. Okay, I know I spent quite a bit of time on this slide, but I want to make sure you're on the right page before we get blasted here. Does everybody follow me on monoprotic, diprotic, and triprotic? I promise I'll ask you some questions soon enough. Okay, great. Thanks, Chris. Thanks, Sierra. Perfect. Again, just kind of getting going here on acids and bases. Well, if you wanted something to memorize, you have to memorize all of these strong acids and weak acids. Okay, so I'll even write that on here for you, just so you're fully cognizant that you have to memorize all of these. Okay, you have to memorize hydrochloric acid, hydrobromic acid, hydroiodic acid. You notice that all of these are halo acids, right? And you're like, what? They all have a halo? Are they holy or something? No, they are all hydrogen bound to what? Bound to a halogen. So it might be a knee-jerk reaction to think that hydrofluoric acid would be a strong acid, but in fact, hydrofluoric acid is a very weak acid. Okay, it's a dangerous acid, super dangerous, to the point where I don't even think I'd work with it. But hydrofluoric acid is weak. The next ones come up quite a bit in general chemistry: sulfuric acid, nitric acid. Perchloric acid, not so much, but that's a strong acid as well. And you have to memorize the other weak acids, which are nitrous acid, phosphoric acid, and acetic acid. Okay, there's no way for me to tell you there's a quick trick that you can learn to know all these in 10 seconds or whatever. There's nothing more that I can tell you than you have to memorize some strong acids when you take general chemistry, right? Everybody has to. Let's look at a problem here. It says classify each of the following species in aqueous solution as a Bronsted acid or base. Who could tell me for A, would this be considered a Bronsted acid or base, HBr? Not a trick question. What do you think? Is HBr an acid or a base? Yeah. I've only got one answer. Does anybody else have an answer? HBr. Yeah. Okay, I got a bunch of people that are saying that HBr is an acid. But look, if we go back here, we see that HBr is hydrobromic what? Acid. So I would say it's probably an acid. Also, what was the definition of a Bronsted acid? A Bronsted acid was an H+ donor. Does HBr have a proton to give up? Absolutely. And so it is an acid. Remember that a Bronsted base is an H+ acceptor. Okay, so with those in mind, the next ion, who could name NO2 minus? Could anybody tell me what that is? This goes back to nomenclature. What's NO2 minus? Yeah, it's the nitrite ion, right? This is nitrite, right? Like that. Would nitrite be considered a Bronsted acid or a Bronsted base? What do you think? Yeah, it's going to be a base. It doesn't have a proton to give up, but it can accept a proton, right? So this is going to be a Bronsted base. And then I'll help you the last one. The last one here, this is called bicarbonate, or hydrogen carbonate. Either one works, okay? And the answer is that hydrogen carbonate could be either, okay? It could be an acid or it could be a base. Now, let me give you an example. If HCO3 minus, if it loses a proton, right, you'd end up with H plus and CO3 2 minus, okay? So that would be it behaving as an acid, but it could also accept H plus. If you have HCO3 minus plus H plus H plus, you get H2CO3. So in that case, it's behaving as a base. And so the answer is the bicarbonate ion could behave as either an acid or a base depending on the situation. All right, let's move on from there and let's talk about neutralization reactions. Neutralization reactions are probably the first reaction that you would learn in acid-base chemistry in any chemistry class in the on the planet Earth, okay? And the general concept that you're going to see in neutralization reactions is that you're going to take an acid, so that means you have to know your acids, you're going to add it to a base, you're going to get a salt and water. I just want to remind you that a base, okay, that generally speaking, if you have a hydroxide is OH minus of a group 1A or 2A metal, okay, it's going to be a base, okay? So for example, since sodium is in group 1A and hydroxide is hydroxide, that's going to be considered a base, okay? So here we have HCl, which is our acid. We're adding it to sodium hydroxide, which is our base. We end up with sodium chloride, which is, it's table salt, yes, but a salt, remember, is a metal and a non-metal in an ionic compound, okay? So that's a salt, plus we end up with water. So this is our molecular equation, right? This is where everything is written as one unit whenever it says aqueous. Here we have our ionic equation. This is our ionic, or sometimes we call this the total ionic equation. What are we doing here? Everything that's aqueous, we're breaking it apart into its ions. And then for the net ionic equation, the net ionic equation, what we do is we cancel out the spectator ion. So you can see that sodium is a spectator. It remains unchanged on both sides, as is chloride. It remains unchanged on both sides. And so we write what's left over. And so most of the time, when you're looking at a neutralization reaction, you end up with H plus, a proton, plus hydroxide gives you water as your net ionic equation. Let's try one together as a group. Now I'm going to cut the screen here a little bit, and I'm going to write a molecular equation. What if we had sulfuric acid, okay, which is a strong acid, and we added that to lithium hydroxide, okay? And then what would we end up with? Well, what's going to happen is our cation is going to combine with the other anion. So we're going to end up with lithium sulfate, which is Li2SO4. It's soluble. I'll skip that part for us. And then you end up with water, okay? So H2, or the hydrogen ions, are going to combine with hydroxide to make water. Now, you probably noticed that this equation is not balanced. Let's do that. You can see that on the left-hand side, I have 1, 2, 3 hydrogens, like that. We could probably make it simpler than that if we started with the lithium, because we have lithium, we have 1 lithium here and 2 lithium here. Let me start with that. So if we have 2 lithiums like this, yeah, then it becomes a lot more apparent that we have 1 sulfur on each side. Now we've got 1, 2, 3, 4 hydrogens, and we have 2 here. So what times 2 gives me 4? And the answer is 2. And so I put a 2, now I put a 2 here. And so now my equation is balanced. Now, what I want you to try to do is to break this apart into its ionic equation, or its total ionic equation. I'll give you a second, but everything that's aqueous should be broken apart into its ions. Okay, well, let's break everything apart into its ions. Since sulfuric acid is a strong acid, we're just going to ionize the whole thing. So we're going to end up with 2 protons, and those are aqueous, plus a sulfate ion, which is aqueous. We're going to get 2 lithium cations from our lithium hydroxide. We're going to get 2 hydroxides from our lithium hydroxide. Lithium sulfate is aqueous, so we're going to have 2 lithium cations, which are aqueous, plus a sulfate ion, which is aqueous, and then we end up with 2 moles of water, which of course is a liquid. And so that is our ionic equation. And now we're going to write out our net ionic equation, and we're just going to cancel out what's the same on both sides. So we have sulfate, we can cancel that out, and we also have lithium, we can cancel that out. And looky, we're left over with H plus, 2 of them, plus 2 hydroxides, gives me 2 moles of H2O, okay? And we can even simplify that, right? Just divide the whole thing by 2, and I would accept either one. But this is the net ionic equation right here, like that, okay? Give me a thumbs up if you follow me on the molecular equation, ionic equation, and net ionic equation. Okay. It's one of those things that even if you can give me a partial thumbs up and just say, yeah, I think I could do it. I might need to practice, but I could do it if I practiced, okay? Now, if we try a neutralization reaction with a weak electrolyte, we're going to take a weak acid plus a strong base. We end up with a salt plus water, but the only thing that changes is the direction of our arrow. Instead of being a one direction arrow, we have an equilibrium arrow, and that's what this denotes, okay? So this is equilibrium, like that, okay? Anyhow, so we have hydrocyanic acid, that's HCN, plus sodium hydroxide. We get sodium cyanide plus water. We break everything apart into its ions. I didn't do it here, though, did I? That's not good. Anyhow, so it doesn't dissociate, though, right? Why does it not dissociate? It doesn't dissociate because it's a weak acid, and so we don't draw it as dissociating, okay? So let's make a note of that, okay? So weak acid, we'll put here, weak acid does not dissociate in our total ionic equation. Dissociate, okay? Anyhow, like that. And so we can still cancel what's the same on each side, right? This is our molecular equation. This is our ionic equation, and this is our net ionic equation. And so sodium is the same on both sides. So what we're left over with is HCN plus hydroxide gives us cyanide plus water, like that. All right, let's try another example. It says here, write molecular, ionic, and net ionic equations for the following acid-base reactions. Well, there's only one of them, so for this acid-base reaction. We have hydrobromic acid plus barium hydroxide. Could anybody tell me what the ionic compound that you would form from this reaction would be? What would be the ionic compound that you would get as a product here? You would get an ionic compound here. Does anybody have an idea what it might be? What's going to happen is your cation and your anion are going to combine, right? They're going to swap places, right? So the barium, which is positive, which is 2 plus, and the bromine, which is -1, those are going to combine, and your hydrogen ion or your proton, which is +1, is going to combine with your hydroxides, which are 2 minus, right? Because there's 2 of them, or we could just put -1, I guess, because the subscript. But anyhow, that's what's happening, right? This is where the water comes from. So you end up with BaBr2, barium bromide, which is aqueous, and you end up with H2O, so plus H2O. Now what's left over to do is to balance the equation. Since we have 2 bromines in barium bromide, we're going to need to put a 2 in front of our HBr, like that. Now we have a total of 4 hydrogens, and so 2 times 2 gives me 4. There's my balanced equation. All right, remember, an acid plus a base gives us a salt plus water. Okay, now for the total ionic equation, or the ionic equation, whatever you want to call it, either one is fine. We're going to break everything apart into its ions. I should point out that HBr is aqueous, as is barium hydroxide. So let's write that out. We've got 2 hydrogen ions in HBr, because there's 2 molecules of it, plus 2 bromides. Those are aqueous. We've got a barium 2+. Why do I know it's 2+? Because it's in group 2A. Aqueous, plus 2 hydroxides. Those are aqueous. We form a barium cation, which is aqueous, plus 2 bromides, which are aqueous, plus 2 moles of water, which is a liquid, I should point out, like that. Okay, so now we're going to cancel everything that's the same on both sides. So the 2 bromides cancel and the 2 bariums cancel. And now for our net ionic equation, we're left over with 2H plus aqueous plus 2 hydroxides aqueous gives us 2 water molecules. And we could even simplify that as we did previously this evening. 2H plus OH minus gives you water, like that. A neutralization reaction. Here's another example of a neutralization reaction, but this one is sulfuric acid and potassium hydroxide. I'm going to leave that one for now. I'm going to skip this one because I want you to take a look at that one yourself. And I want to go right ahead to this one here, which shows you the neutralization reaction between hydrochloric acid and sodium carbonate, right? This is sodium carbonate, okay, to produce sodium chloride, which is a salt, and water, but we also end up with a gas, okay? So CO2 is a gas, and whenever you have a carbonate as your base, so metal carbonates like potassium carbonate, lithium carbonate, calcium carbonate, sodium carbonate, those are all bases. And so whenever you react an acid with a carbonate base, you always end up with carbon dioxide as a gas, okay? So the same thing applies. We break it apart into its ions here in the total ionic equation, and we cancel the ions that are the same on both sides, like that. And we end up with 2H plus carbonate gives us H2O plus CO2 in our net ionic equation. All right, that's quite a bit of talk about neutralization reactions in the acid-base section of chapter 4. But before we end our lecture, I want to make sure that we spend a little time talking about oxidation reduction reactions this evening. I just want to get you started on this so that you're initiated to the idea of what an oxidation reduction reaction is. The first thing I'll say about oxidation reduction reactions is that sometimes we call these redox reactions. The redox reactions, if you're the kind of person who likes to look up more content on YouTube or maybe in another textbook, you might look for redox reactions. Another thing I'll say is you can't have one without the other, okay? You can't have oxidation occurring without reduction, and you can't have reduction occurring without oxidation. Another description of oxidation reduction reactions is what we call electron transfer reactions, okay? And if you look at this reaction that's being shown here, this is magnesium burning, Okay, and I'm sure that some of you have tried this before. So if you take a piece of magnesium, so this is magnesium burning, I should say, combustion, combustion of magnesium, like that. What happens is you take magnesium and you burn it and you combine it with oxygen and you end up with this here, which is magnesium oxide. Now, what the heck is happening here? Okay, what's happening is you're taking magnesium metal, right? When it says magnesium solid, that's plain old magnesium. Okay, just a plain old piece of magnesium metal. It's got no charge, right? No charge at all. And what happens in the reaction, you end up with MgO. Well, what happens in the reaction is that the two magnesium atoms lose a total of 4 electrons, so that you end up with 2 moles of Mg2 plus. By the way, I should tell you that these are all reversed for some reason. This should say 2 plus, and this should say 2 minus. It's kind of minutia, but it's irritating for me as a chemistry instructor. Anyhow, so we have the 2 magnesiums, and we end up losing a total of 4 electrons, okay? And if you're like, why is it 4 electrons? Well, it's because if you take magnesium as a solid, right, and you make magnesium 2 plus, okay, well, how did you get a positive charge? It must have lost something that was negative. You lose a total of 2 electrons. So that means if you take the whole dang thing and you multiply it all by 2, you end up with this equation right here. 2 magnesiums gives you 2 magnesium 2 plus what? 4 electrons. 2 times 2 is 4, okay? So that's where that comes from. And then what's happening to the oxygen? Well, oxygen, when it's pure, I'm breathing air right now, and I'm not getting a shock. I'm not feeling anything charged in the air, right? Because oxygen is an uncharged molecule. But what happens is it gains those 4 electrons to become O2 minus. Then you have an anion and a cation, and they combine to make this ionic compound. How did you know it was an ionic compound, Mr. Dion? Well, because magnesium is a metal and oxygen is a non-metal, right? Okay, now it says here in the parentheses the oxidation half reaction. So oxidation is the loss of electrons, and then in the reduction half reaction is the gaining of electrons. Now you might be wondering, what the heck is a half reaction? How do I do that? Well, a half reaction is just isolating one part of a reaction and demonstrating what's going on together. So literally, if you add these 2 equations together, these 2 reactions, look what happens. The 4 electrons cancel on both sides like that, and you're left over with 2 magnesiums plus oxygen gives you 2 magnesium ions and 2 oxygen ions, which combine to give you 2 moles of, or 2 formula units, whatever you want to think of magnesium oxide, like that. Another kind of mnemonic that's very popular with students is oil rig. Oil, which stands for oxidation, is losing electrons, and rig stands for reduction, is gaining. It's gaining electrons, like that. In Canada, we always learned Leo says Gur. Leo the lion says Gur, which is loses electrons, oxidized, gains electrons, reduced. Either way, either one is fine. But oxidation and reduction are like love and marriage. You can't have one without the other. So it says here are some examples of redox reactions. In this first picture, you can see a picture of, this is actually a bar of zinc. Let me see if the green pen out here. So this is zinc metal, just a pure bar of zinc, and it's in a solution of copper 2 plus ions. Now it's probably copper sulfate. Oh yeah, it says right here it's copper sulfate. So you have Cu2 plus ions, and you have SO4 2 plus, or sorry, SO4 2 minus ions. And what happens here is that the zinc is going to get oxidized. So it's going to lose its electrons, right? Oxidation is losing. So it's going to lose 2 electrons to form zinc cations, which is going to result in a new solution of zinc 2 plus and SO4 2 minus. But what's going to happen is the copper that was here as ions is going to gain those electrons and become copper metal. So if you look at all this kind of dark colored crust that's on the zinc bar, that's copper that actually precipitated out of the reaction mixture. So it will adhere to the surface of the zinc bar until the zinc completely deteriorates. Here's another example. It says when a piece of copper wire, so this is a piece of copper wire right here, is placed in an aqueous solution of silver nitrate. So this has silver cations and nitrate ions. Okay. The solution of Cu2 plus and H ions is the silver ions are converted into solid silver. So what happens here is that the copper is going to lose electrons, right? It's going to get oxidized, and in the process, the silver will gain electrons, and it ends up depositing. Okay, so it basically ends up precipitating. So that's oxidation and reduction, and those are two examples of redox reactions. Here's another one. If we just look at this reaction here, and this is just the formula, or sorry, the reaction written out for what occurred right here, is that we take zinc and we combine it with copper sulfate. We end up combining the zinc with the sulfate. So zinc combines with sulfate, and then copper comes out by itself. And then the copper comes out here, okay? And if you think about what's happening, right, zinc metal doesn't have any charge, right? You can even write zinc 0 if you want, okay, as a means of electron bookkeeping. Well, when you have zinc in zinc sulfate, that's an ionic compound, right? Zinc is a metal, okay? And the sulfate polyatomic ion is all made of non-metals. Okay, well, what's the charge of zinc in zinc sulfate? It must be zinc 2 plus, and the sulfate must be 2 minus, right? Because sulfate is always 2 minus. There's no exceptions to that. So that tells you that the zinc must be 2 plus. Now, how did zinc become zinc 2 plus? It had to lose 2 electrons. So that means the zinc is being oxidized. Also, this should be 2 plus. It's in the wrong order, but whatever. So we could say that zinc is being oxidized, right? Oxidation is losing. You could also say that zinc is the reducing agent. What do you mean by a reducing agent? Well, what I mean is that zinc is affecting the reduction of copper 2 plus. Okay, so zinc is going to affect the reduction of copper 2 plus. What does that mean? Well, that means that zinc is providing the 2 electrons that are going to be used to reduce copper 2 plus to copper metal like that. So we can say that the copper 2 plus is reduced, or we can say that copper 2 plus is the oxidizing agent because it's causing zinc to be oxidized. Give me a thumbs up if you follow me on that. Oxidation and reduction. Yeah? Does anybody follow me on that? Redox, yeah. One of those things that might take a little bit of time to wrap your head around, you know, and really do some practice to make sure that you understand oxidation and reduction. Okay, before we end the lecture, I just want to go over one more concept with you that I want to introduce before Thursday's class, and that is the concept of oxidation number. And the reason I want to introduce it to you is because there's a bunch of rules that you have to know in order to solve for oxidation numbers, and I can guarantee you I'm going to ask you questions about oxidation number on your next exam. Now, oxidation number is nothing more than the charge that an atom would have in a molecule or an ionic compound if the electrons were completely transferred. And so when you have something like zinc sulfate, ZnSO4, right, it's like, what's the charge of the zinc, okay? What's the charge of the oxygen? What's the charge of the sulfur? And you might be thinking, well, I know the charge of the zinc. You already told me, like last slide, that it was 2 plus. I told you what the charge, and I would say, yeah, you're absolutely right. I told you what the charge of SO4 2 minus was, but what's the charge of the actual oxygen atom? All right, what's the charge of the actual sulfur? Okay, and that's what we're going to work towards with these rules. Okay, so let's move on from there. There we go. Okay, so here are the rules. Get ready, strap your skates on. So the first one is free elements. So if you have any element on the periodic table and it's uncombined state, that means it's not in a compound, okay? It's got an oxidation number of 0. If you had sodium, beryllium, potassium, lead, hydrogen, oxygen. Remember, hydrogen and oxygen are diatomic elements. Phosphorus is a tetratomic element, but any element in its pure state is just 0. Okay, so that's rule number 1. The next one is one that I just mentioned, is if you have a monatomic ion. So if monatomic just means one atom and it's an ion, so copper, oxygen, whatever, doesn't matter, okay? the oxidation number is equal to the charge on the ion. So if you have lithium +1, well, it's got an oxidation number of +1. If you have iron 3+, it's got an oxidation number of +3, right? If you have O2-, it's got an oxidation number of -2. Okay, nothing more than that. The next one is kind of a funny rule because students usually don't like rules that say things like usually, okay? But the oxidation number of oxygen is usually going to be -2. There are a few exceptions to that, like superoxides, but I'll get to that in a second. Anyhow, so one of the exceptions is right here. This is H2O2, which is hydrogen peroxide. It's I don't know why it says O2. That's not right. Anyhow, we'll just put it as H2O2. It's -1. All right. So that's an exception. The next one is the oxidation number of hydrogen is +1 unless it's bonded to a metal in a binary compound. In these cases, the oxidation number is -1. I'll give you some examples of that. The next one is if you have a group 1A metal, a group 2A metal. A group 1A metal will always be +1. A group 2A metal will always be +2. And fluorine will always be -1. No exceptions to that one. The next one says that if you have a bunch of oxidation numbers, the sum of all the oxidation numbers of all the atoms in a molecule or an ion is going to be equal to the charge on the molecule or ion. That's fair enough. And then the last rule is this: the oxidation numbers do not have to be integers. The oxidation number of oxygen in the superoxide ion, O2-1, is 1/2, right? Since you have 2 oxygens and you have a total charge of -1. An example of that would be like this, KO2, that's potassium superoxide. The charge of potassium is going to be +1 because it's a 1A metal, and the oxygen has to be -1 overall, and there's 2 of them, so 1 divided by 2 would give you 1/2, okay? Anyhow, -1/2. All right, well, with that in mind, let's take a look at a quick example or two, and then we'll call it quits for the evening. The first one says, this question says, assign oxidation number to all the elements in the following compounds and ions. So we have lithium oxide. Well, lithium is a group. This is from group 1A. And so lithium is going to be +1. There's no exceptions to that. Now, if I have 2 lithiums, right, I have a total charge of 2+ or +2, however you want to think about it, okay? We'll put 2+. So what must the charge of oxygen be? It has to be 2-. And in fact, oxygen usually is 2-. If we go back here, we see that oxygen is usually 2-. Okay, well, there we go. Oops. There we have it. So oxygen in this one is 2-, like that. So those are the oxidation numbers. The next one is nitric acid. This one gets a little bit more interesting, okay? So follow me carefully here. Hydrogen is almost always +1, and that makes sense because the polyatomic ion nitrate is -1, right? Nitrate NO3-, okay? So that makes sense, but now we want to dissect the NO3 ion. Okay, we've already decided that hydrogen is +1. What about the NO3- ion? Remember, the sums of the oxidation numbers of the 3 oxygens and the nitrogen have to equal -1. Now, oxygen usually has a charge of -2. So if it's 2- and there's 3 of them, right? -2 times 3 gives you -6. So what must the oxidation number of nitrogen be if the total charge of the ion is -1? Can anybody answer that? What plus -6 gives me -1? Does anybody have an idea about this one? Yeah, it's +5, exactly. Yes, so it's +5, like that. So that means your hydrogen is plus, your oxygen is 2-, and your nitrogen is 5+, like that. Okay, I'm going to save the last one, which is the dicarbonate ion, for our next lecture, and you can try it before then. I would highly recommend it.